Greetings, welcome to today's class. So we have been looking at frequency response methods. In the previous class we looked at stability margins, what was called as relative stability, right, and how to essentially characterize system performance using gain margins, phase margins and so on, right. So in that connection, like today we will essentially learn how to design a controller which is called as a lead compensator using frequency response methods. Okay, so that's going to be the objective of today's class. So we'll consider the standard feedback loop that we have been dealing with in this particular course. So we consider unity negative feedback. This implies that the feedback path transfer function h of s is going to be 1. So that is the implication. C of s is the controller transfer function and P of s is the plant transfer function. So now what does a lead compensator do, right? So typically what a lead compensator does is that it adds a sufficient amount of phase lead to reduce the excessive phase lag, okay, if any, that is associated with the uncompensated system, right. So excessive phase lag associated with the uncompensated system. See, typically like we can have a plant which does not have a significantly high phase margin, for example. Then what happens is that the lead compensator adds phase to the system or plant and ensures that the phase margins are essentially driven to a level which is acceptable, right. So that is what a lead compensator does, and by and large it usually improves the transient response. We are going to see how, but it may also amplify high frequency signals. Okay, so in some cases, so it can amplify high frequency components, okay, in the output. So that may be an issue, particularly if you have noise, for example, high frequency noise, for example. We will see how these points can be addressed, right, as we go along. So let us look at the structure of the lead compensator. So typically the transfer function of a lead compensator takes the form C of s is equal to Kc alpha times Ts plus 1 divided by alpha times Ts plus 1. So this can be rewritten as Kc times S plus 1 by T divided by S plus 1 by alpha T. Okay, so that is the structure of the lead compensator. So here alpha is what to say, positive real number between 0 and 1, and of course T is greater than 0 and Kc is also greater than 0. Okay. So immediately we can observe that the lead compensator introduces an open loop pole and an open loop 0. So one can immediately observe that the lead compensator introduces an open loop 0 at minus 1 over T and an open loop pole at minus 1 over alpha T. Okay, so that is what happens in a lead compensator. So it introduces an open loop 0 at minus 1 by T and an open loop pole at minus 1 by alpha T. Okay, so now let us analyze the sinusoidal transfer function associated with this lead compensator. So essentially we substitute S equals j omega and see what happens, right. So, then C of j omega becomes k c alpha times 1 plus j times t omega divided by 1 plus j alpha t omega. Okay. So, this can be rewritten as k c alpha divided by 1 plus alpha square. Of course, we need to do it carefully. This will become k c alpha. Of course, what I am doing is that let me explain what I am doing here. So, I am just multiplying and dividing by the conjugate. So, if I multiply and divide by 1 minus j alpha t omega, so what we are going to get is the following: k c alpha times 1 plus alpha t squared omega squared divided by 1 plus alpha square t square omega square plus j times k c alpha t omega times 1 minus alpha divided by 1 plus alpha square t square omega square. Okay, so that is what we will get. Okay, so that is the real component and the imaginary component of the sinusoidal transfer function associated with the controller transfer function of a lead compensator. Okay. So, before we look into this, like from the what to say from the function c of j omega, we can immediately observe that the magnitude of c of j omega is nothing but k c alpha times square root of t squared omega squared plus 1 divided by square root of alpha squared t squared omega squared plus 1, and the phase of c of j omega is going to be tan inverse of t omega minus tan inverse of alpha t omega. Okay, so that is what will happen to the phase of this transfer function c of j omega. Okay, so we can immediately observe that the phase of c of j omega is always going to be greater than or equal to 0 for all omega, right. So, that is something which we can observe, right. So, for all frequencies, the phase is going to be non-negative, right. So, that is something which we can immediately observe. And also, if you look at the structure of the transfer function, we can immediately see that the corner frequencies of the transfer function corresponding to a lead compensator are at 1 by t and 1 by alpha t. Okay. So, those are the two corner frequencies associated with the lead compensator. So, anyway, we will use these corner frequencies in plotting the Bode diagram, right, corresponding to this transfer function. So, now if we look at the what to say real and imaginary component of c of j omega, we can immediately notice that the value of c of j omega at omega equals 0 is just k c alpha, right, because the imaginary component vanishes, and as omega tends to infinity, once again the imaginary component vanishes and c of j infinity is just k c. Okay. So, we can immediately observe that the transfer function c of j omega, the sinusoidal transfer function c of j omega starts on the positive real axis for omega equals 0 and ends on the positive real axis at as omega tends to infinity, right. So, that is an observation we can readily make from this particular equation, right. Now, this is something which I am going to leave as homework. Okay. One can easily show that. So, if you take the real component, which is k c alpha times 1 plus alpha t squared omega squared divided by 1 plus alpha squared t squared omega squared minus k c by 2 times 1 plus alpha, okay, whole square plus the imaginary component square k c alpha t omega times 1 minus alpha divided by 1 plus alpha square t square omega square whole square, that is going to be equal to kc by 2 times 1 minus alpha the whole square. Okay. So, that is something which we can show, you know, like so I am going to leave this as a homework exercise, pretty straightforward. Okay. So, one can easily show that this is true, right. That is, we subtract kc by 2 times 1 plus alpha from the real component, square it, and then take the imaginary component, square it, and then add the two resulting quantities, we will get kc by 2 times 1 minus alpha whole square, right. So, this immediately tells us that the locus of the sinusoidal transfer function c of j omega is going to be in the form of a semicircle, which is going to essentially have its center on the positive real axis at kc by 2 times 1 plus alpha, and having a radius of kc by 2 times 1 minus alpha, right. So, that is essentially an equation of a circle, right. So, we can immediately observe that the locus of c of j omega is a semicircle of a radius kc by 2 times 1 minus alpha that is centered at kc by 2 1 plus alpha comma 0. Okay. So, that is what happens in the case of the locus of c of j omega. Okay. So, that is the what to say structure or shape of the particular transfer function that we are considering. Okay. So, let us plot the Nyquist plot for this particular transfer function. Okay. So, if we plot the Nyquist plot, okay, let me consider the real and the imaginary axis. Okay. So, we can immediately observe that one thing, right, from the real and the imaginary components of c of j omega, we can readily observe that for all omega between 0 and infinity, right, the real part is always going to be positive and the imaginary part is also going to be positive, you know, like except at the limiting values of 0 and infinity, right. So, as a result, the Nyquist plot of this particular function is going to be in the first quadrant, right, in the complex plane. So, let us call this complex plane as the C of S plane. So, in the C of S plane, so we can immediately see that the value of the sinusoidal transfer function is at kc alpha, right, and it goes to kc as omega tends to infinity, and the center of the circle is going to be at the middle, which is kc by 2 times 1 plus alpha. Okay. And what is going to happen is that the locus of this curve, the Nyquist plot is going to be a semicircle. Okay. So, that is what is happening. So, this is the Nyquist plot for this particular transfer function. So, this is where it will start as omega equals 0 and this is where it goes to as omega tends to infinity, right. So, let me write it here. Okay. So, this is the place where it starts at omega equals 0. Now, we can immediately observe one thing, right. So, if I want to figure out, of course, we can immediately see that the radius of this semicircle is going to be kc by 2 times 1 minus alpha, right. So, that is already some which is known, and we can immediately observe from this Nyquist plot that the face of this particular sinusoidal transfer function is always going to be non-negative, right. Of course, it is 0 at omega equals 0 and omega tending to infinity. For all other frequencies, it is positive, right. And the maximum phase angle which can be obtained from this particular transfer function can be figured out by drawing a tangent from the origin, right, to this semicircle. Okay. And if we look at this particular line segment, that is going to be the radius of the length of the line segment is going to be the radius of this particular semicircle, right. So, now let us call this angle as phi m, okay. So, let me write it here. So, this is phi m. So, what is phi m? Phi m is going to be the maximum phase lead provided by the lead compensator at a frequency which we denote by omega m. So, okay, so what is omega m? Omega m is this particular frequency, you know, like wherever it provides the maximum phase, you know, like that is essentially omega m. Okay, so phi m is the maximum phase angle, right. So, we can immediately observe that. So, we can immediately note that it is pretty straightforward to calculate phi m. We see that sine of phi m is going to be equal to kc by 2 times 1 minus alpha divided by kc by 2 times 1 plus alpha. So, this will essentially give me 1 minus alpha divided by 1 plus alpha, right. So, that is what I am going to get for phi m, right. Now, we can also observe that tan phi m, which is going to be the opposite divided by the adjacent side, and the length of this adjacent side is going to be kc times square root of alpha, right. So, because this is a right angle triangle, so you can use the Pythagoras theorem to figure out the length of this what is a line segment from the origin to the point where the tangent touches the semicircle. That is going to be kc times square root of alpha. So, as a result, tan phi m is going to be equal to kc by 2 times 1 minus alpha divided by kc times square root of alpha. So, this will give us 1 minus alpha divided by 2 times square root of alpha. Okay. So, that is what we will get for tan phi m. Okay. Now, as a next step, let us find omega m. So, what is omega m? Omega m is the frequency at which we get the maximum phase angle, right. So, for that, you know, we just need to essentially go to the expression for the phase of the sinusoidal transfer function c of j omega. Please recall that the phase of c of j omega is going to be tan inverse of t omega minus tan inverse of alpha t omega. Okay. So, this implies that phi m is going to be equal to tan inverse of t omega m minus tan inverse of alpha t omega m, because we get the maximum phase angle of phi m when the frequency is omega m, right. So, that is what we are using. So, this will immediately tell us that t omega m minus alpha t omega m divided by 1 plus alpha t square omega m square is going to be equal to tan phi m, which is nothing but 1 minus alpha divided by 2 times square root of alpha, right. So, we just are using the trigonometric identity for expression, you know, like which essentially relates tan inverse of a minus tan inverse of b, right. So, that is what we have essentially used, right. That trigonometric formula has been used. So, with this expression we can immediately observe that we can get a quadratic equation in omega m square as follows. So, omega m square times 1 minus alpha times alpha t square, right, minus omega m times 2 t square root of alpha times 1 minus alpha, okay, plus 1 minus alpha, that is going to be equal to 0. Okay. So, that is the equation we are going to get for omega m. Okay. So, one could solve this equation. So, solve this equation to obtain omega m as square root 1 divided by square root of alpha times t. Okay. So, this is something which I am going to once again leave you as a homework exercise, right. So, we see that the maximum phase is obtained at a frequency of 1 divided by square root of alpha times t, right. Now, if you recall what were the two corner frequencies, right. The two corner frequencies were 1 by t and 1 by alpha t. So, we can immediately observe that omega m is the geometric mean of the two corner frequencies, right. So, that is something which we can observe from this expression. So, we can observe that omega m is the geometric mean of 1 by t and 1 divided by alpha t. Okay. So, that is something which we can immediately find out, right, from this expression.